You probably know this already, but in this lecture, we learn once again why we do not specify a softmax activation function directly in the final layer of our convolutional neural network. Now that we've set up all the layers of our convolutional neural network, we are ready to set up our objective function or cost function. The cost function for classification algorithms is typically the cross entropy. The cross entropy measures the difference between two probability distributions. The cross entropy is the same objective function that we used when we set up our logistic regression model. If you remember, when we set up the logits layer in the last lecture, we hadn't specified the softmax activation function. We had let activation remain none for that dense layer. This is because the TensorFlow library tf.nn.sparse softmax cross entropy with logits includes the softmax activation function within it. So when you use this particular TensorFlow library function, you do not need to specify a separate softmax activation for your logits layer. The logits layer is the input to this function. In order to calculate the cross entropy, we also need the actual y labels, which is another argument into this function. The remaining steps should be familiar to you from the regression models that you've built. We'll calculate the loss by calling tf.reduce_mean on our cross entropy calculation. We'll set up a gradient descent optimizer. Here we choose to use the Adam optimizer. The Adam optimizer is a momentum based optimizer and often gives better results than simple gradient descent. The training phase of our neural network seeks to minimize the loss function, which we do by calling optimizer.minimize on loss. Remember that the output of our softmax layer is a set of probabilities. The probability that our input image is one of the digits 1 through 10, where 10 is the label for the digit 0. Check if the predicted label of our neural network is equal to the actual label for that image by using tf.nn.in_top_k. So we basically want to see whether our top prediction or the digit with the highest probability score from our softmax activation layer is equal to the actual label y. We can measure the accuracy of our predictions by simply calling tf.reduce_mean on our correct predictions. Now, this image data has to be fed into our neural network in batches, which means we require a helper function which will allow us to get the features and labels for one batch at a time. We'll call this the get next batch function, which takes as an input argument the batch size. The current iteration variable, which we've initialized to 0, will track the global batch index, which batch we are at any point in time. Once we have the value of the current iteration, we can use some simple math to find the start index and the end index for the current batch. Notice the modulo len though. If the start index of a batch goes beyond the last index of the training data set, we loop back to 0, we reset to 0, which is why this modulo len exists. Using the start and end indices that we've just set up, extract the training images and the corresponding labels for a single batch. Once this is done, you can increment the value of the current iteration. This is our global variable, and then return the images and the corresponding labels for this batch to the caller of this function. We'll run our training for 10 epochs, that is 10 passes through our training data, and we'll use a batch size of 100. Instantiate a session that will execute our computation graph and initialize all our variables. Remember that we are using only about 10,000 instances from our training data. We are not using the entire training data set. So the number of examples can be gotten by finding the length of our y labels. We iterate through 10 epochs, and for every epoch, we run through all the batches in our training data set. We'll use the get next batch helper function in order to get the current batch of images and the corresponding labels, and we'll call session.run on our training operator. Use the feed dictionary to feed in values for the x and the y placeholders. At the end of every epoch of training, evaluate the accuracy of our predictions on our training dataset as well as on our test dataset. This will allow us to see how this neural network training converges. Print out the training accuracy as well as the test accuracy to screen. Go ahead and hit Shift Enter to execute the code within the cell and let the training for your neural network commence. Notice how training accuracy steadily increases. Test accuracy is also increasing, but far more slowly as compared to training accuracy. At the end of the 10th epoch, the test accuracy is 69.5%, which isn't bad. This might seem a little low to you, but don't forget that we are trying to classify 10 digits. So it's not a binary classifier where it's just a true or a false, where if you pick at random, you'll immediately get 50% accuracy. The digits have to be identified as 10 different types. So 69% is actually pretty good considering we used a really small data set and trained for just 10 epochs. Since we do have a lot of training data that we haven't used yet, let's increase the size of our training data as well as test data. We'll now work with 15,000 images in our training data set and use 1500 images in our test data set. Now, the number of images in our test data doesn't really contribute to improving our machine learning model. It's the increase in the size of our training data set that will make the real difference. Go ahead and hit Shift Enter on all of the code cells and run training on this model once again. We start off with a test accuracy of 45%, which immediately jumps to 64%. So the improvement has been rather rapid. And at the end of the 10th epoch, we end up with an accuracy of 76.4%. We just increased our training data set slightly and got this massive improvement in our prediction accuracy. Now, I've kind of picked this convolutional neural network architecture at random. There's something for you to try at home. Change around the architecture of the CNN, add a couple of pooling layers, add more convolutional layers, and run with all 70,000 training images and see what accuracy you can come up with. Typically, while using TensorFlow, we set up the last layer as a logits layer where activation is set to none. This is because in TensorFlow, the softmax activation is specified as a part of our objective function, the cross entropy. The sparse softmax cross entropy with logits library function takes in a logits layer, which is a dense layer with no activation, and applies the softmax activation.